Welcome to this video. Today, we are going to take a closer look at two of the most common CT dose metrics, CTDI and DLP. You often see these numbers on CT scanners or dose reports, but what do they really mean and how do they relate to dose? Let's dive in. First, let's start with CTDI, or Computed Tomography Dose Index. CTDI measures the radiation output of the CT scanner, in other words, how much radiation the scanner is producing. The measurement is done using a phantom, either a 16 cm head phantom or a 32 cm body phantom, and a 100 mm or 10 cm ionization chamber. The chamber is placed in both the center and periphery positions to measure dose distribution across the phantom. CTDI is used to characterize scanner performance and helps us compare dose levels across different scanners or protocols. There are a few different CTDI metrics you'll see. CTDI 100, which is the normalized dose profile along the z-axis. CTDIw is the weighted average across the phantom. And CTDIvol, which adjusts for the table pitch during helical scanning. We'll go into those next. Let's break this down. CTDI 100 is the basic measurement. It captures the dose profile along the z-axis using a 10 cm pencil chamber. The chamber integrates the total dose over 10 cm length, and we normalize this to the length. This gives us CTDI 100, a value in milligray. Next, we have CTDIw, or weighted CTDI. This combines the center and periphery measurements to give an average dose across the entire phantom. The formula is CTDIw equals to 1/3 of the central measurement plus 2/3 of the periphery measurements. Finally, we have CTDIvol. This adjusts for the pitch of the scan. If pitch is less than 1, the table moves more slowly. Slices overlap. This results in higher dose, and therefore CTDIvol goes up. On the other hand, if pitch is greater than 1, the table moves faster, meaning there are gaps between slices, and therefore it results in lower dose, and CTDIvol goes down. So dividing CTDIw by pitch gives us CTDIvol, a consistent volume averaged dose per length. Next, let's look at DLP, or dose length product. DLP equals to CTDIvol times the scan length. This gives us an estimate of the total radiation output for the entire scan. It's reported in units of milligray cm. DLP is often used as a rough estimate of total exposure, although it is still not a direct measurement of effective dose. How to interpret the CT dose reports? Now let's take a look at a real-world example, a CT dose report. This report is generated by the scanner after each study, and it typically lists series number, scan type, CTDIvol, DLP, and the phantom size used. It's very important to remember that phantom size affects CTDIvol. For head CTs, the scanner uses a 16 cm phantom. For chest or pelvis CTs, the scanner uses a 32 phantom. When comparing CTDIvol values across different scan types or protocols, you always need to check which phantom size was used. Otherwise, the values aren't directly comparable. Another point, you don't need to measure CTDIvol for every possible scan combination. Since there is a non-linear relationship between scanner output and MAS, CTDIvol can be calculated based on standard measurement and scaled accordingly. It is always important to look at both CTDIvol and DLP together, and to always be aware of which phantom size was used. So here are the key takeaways. CTDIvol tells us the scanner output per slice in milligray. DLP tells us the total radiation delivered across the scan length in milligray times cm. Neither is a direct measure of dose, but together they help us monitor and optimize CT radiation exposure. And always check the phantom size when interpreting CTDIvol. Thank you so much for watching. If you found this helpful, please like, subscribe, and leave a comment. And stay tuned for more videos on CT physics and medical imaging.